webinar of the weekend. It's entitled, It's About Time, What New Measurements Reveal About Audio Quality. We'll be hearing from Michael Ritchie, the Senior Director of Electroacoustic Engineering at xMEMS, and Jacob Sondergaard from Headacoustics. And we'll be learning a little bit about xMEMS, transducers, and as well as how they benchmark using MDAQS, which is a new measurement system that we're probably going to be learning quite a bit about. So please join me in welcoming them today.
Thank you guys. I don't know if we need a mic. Can you guys hear us in the back? Hey Jude.
Hey, what's up, Jake?
Hey. We're good on audio? Michael?
I've learned to enunciate in thespian class in the 9th grade. How am I doing?
So we figured we better start by telling us a little bit about ourselves. Michael, why don't you go first, please?
Being an audiophile and a sound engineer, I've been messing around with semiconductor test since the 80s. And in 2012, I discovered MEMS microphones were being tested at the wafer level, and it blew my mind, so I asked the company who was fabricating them if I could please work for them. So I was a field application engineer for MEMS microphones starting in 2013 and helped the inception of MEMS microphones into the market over the course of about 8 years. And I joined xMEMS 3.5 years ago and been working now on the other side of sensing, actuation. So now we're on actuation. Now we can move air with MEMS diaphragms instead of just sense air with MEMS diaphragms. So now we're making sound with silicon.
So my path into the industry is a little bit different. I was sort of born into it. I've been working in the industry before I was even allowed to work in the industry, and it's been all about acoustics and audio for me. And then from a sort of a personal standpoint, I have someone near and dear to me that's visually impaired, and so audio and the way to communicate and use sound has always been very important to me. And so, along with the joy that music and audio just generally brings to my life, I also have a personal motivation and a drive to really dive into the field of audio. But I've been in the test and measurement side of audio for about 15 years, working for a small company called Brass Sound and Vibration. And for the last 8 years, I've been with a company called Headacoustics. And the common denominator for those two companies is they both specialize in what they do within the field of test and measurement within acoustics. So we're here because, well, a lot of reasons, but there's been a lot of changes in the audio industry over the last little bit. We'd like to play a little video here that might...
You can plug this into your 3.5 millimeters live. Thank you.
Try this. I want to play a little video just to give you a sense of...
Who are we going to see on the video, Jay?
So this is going to be our senior VP at Headacoustics, Wade Bray. He's been in the industry for 60 plus years, it seems like. I think he shows up at work. I think we stopped paying him and he still shows up. He just loves it so much. But he did a video for us not too long ago, a little bit Dr. Seussian, where he just explains a little bit how a lot of us in this field are passionate about audio. So let's see if we can get this to play.
Hey Tech Leads, this is Monday Dev, a platform to manage your entire product development lifecycle.
Still coming out of here.
Yeah. Coming out of there.
The following is said with a twinkle of an eye, my colleagues at More of the sounds that you'll hear by Wiz W. Bray. In quite many places there live engineers listening, wondering, what sounds do I hear? What thing do I call this? A rattle or buzz? A shake or vibration? A fiddly plonk buzz? Whenever I listen, a new thing appears. What thing do I call all these things in my ears? I'm happy to say there's a class on the way. Learn how to listen, describe what you hear, and testing those products will cause no more fear. With critical listening and maybe a filter, acoustic analysis won't feel off-kilter. But who would the teacher be? What could he say? Why, none other than me, Wiz W. Bray. For $100 and maybe some tax, we'll give you the answers, no bull, only facts. Over the sounds that you'll hear, over the graphs you'll create, you'll make your head supervisor think that you're great, and with good reason. So sign up today for our new on-demand class from the brains at Headacoustics. You'll be such a blast.
That is our dear Wade Bray. Thank you.
So what's important about what Wade was saying is, we're in test and measurement all the time, measuring these things. But at the end of the day, we have to use our ears. These are the best microphones we have access to, and this is the best DSP in nature that we're aware of. And so we'll be measuring the lab with metal tube couplers and ear simulators, looking at graphs and charts. Those are just guidelines. Those are just traffic signs along the journey of working with audio equipment. At the end of the day, I always tell our field application engineers when they go through the training course, listen, then measure. Don't measure and then make a conclusion based on looking at a graph. That's not the right way to go about things, and so we're going to try to present today how we're kind of advancing test and measurement to include human listening and biologic hearing function, instead of just throwing something on a bench with a metal tube coupler and going, eureka, we have it. You probably don't have everything you think you have.
Yeah, so we were planning this presentation, and we were thinking we better hire a couple of auctioneers to get to speak on our behalf, because we have a lot of content we got to get through in 1 hour. And so I think in advance we're going to apologize if we're maybe skipping a couple of details along the way or jumping through things, because we got a lot to get through. But the good thing is Michael and I will be here for the duration of the show. So please come and find us. We'll be probably walking around together quite a bit as well if you want to discuss further. Now, to put things into perspective, audio has undergone a bit of a generational technology shift, much like video did. And going back to old dynamic drivers, we had sort of this content upgrade with Dolby Atmos and high-res audio, spatial audio, lossless streaming, and lossless audio files. And now we're seeing a new form of technology in sound transduction in the form of MEMS-based microspeakers. Similarly, we would argue that audio testing has also undergone a bit of a technology shift or generational shift. So without spending too much time on this, you might know this is a 711 coupler. It goes back to late 70s, early 80s, replacing the old Swiss Locky coupler. But this was technology that was designed to basically cover sort of a wideband type of measurement range, about 8K, maybe 10K if you were lucky. And then sort of on the mechanical side, on the hardware side, there was some advances that started pushing the frequency ranges higher, making it more consistent, more stable. And we're getting into something that looks and feels a lot more anthropometric, a lot more human-like. We're getting closer to representing the human being from a physiological standpoint. Then our friends over at B&K in about 2018 came out with what is now, they call it the 5128, but their latest mannequin, which really the innovation in the mannequin is the ear canal representation. So now we're not just talking about an anthropomorphic pinna and concha, we're also talking about the ear canal and the eardrum representation being more anthropometric and human-like. So from a physiological standpoint, we're now better able to measure at the eardrum of the average human being. And so here's a cross-sectional diagram. You can see how the ear canal, the double bend of the ear canal is represented there. And all this is done to where the curves and the frequency responses and the transfer impedances of that ear canal still represents the average human being. So we're getting something that geometrically looks like a human and acoustically behaves a lot more like the average human being. This is great, but...
May I add something on the last slide?
Sure.
Just real quick. I think it's important to notice this geometry here is not a plain wave metal tube like a 711 coupler, and it doesn't have the inherent resonances. But they did MRIs on people's ears. They actually put humans in an MRI machine, and they did a lot of photography, optical character recognition. They wanted to know what happened after the first bend in your ear to your eardrum. So that's modeled off of actual humans over a cross-section of men, women, and actually some younger teenagers, just to get these geometries. So they're not off of one sample size of one person, cross-section of several hundred people.
So that's just one element to the transformation of the industry on the test and measurement side. That's from a geometric standpoint, from a physiological standpoint. Now, I have a friend in the business, Dan Foley. There he is. And Dan, I remember saying years ago that human beings and human brains and human ears are not FFT analyzers. They're more like time waveform analyzers. And as we start to consider some of these new technologies from the transduction side, like the microspeakers and what they are capable of, and Michael will expound on that a little bit later, we also have to consider what is it that we want to capture when we're measuring an audio response? And is there more to it than just measuring at the eardrum and the physics of what happens at the human eardrum? From a frequency perspective, is that enough to really characterize what's going on? So the analogy that I like to draw on when it comes to audio quality is, if I am asking you to evaluate a car and its performance, I think a lot of people might jump to a lot of conclusions on its performance based on the shape of and the appearance of the car. How aerodynamic does it look? How many doors does it have? What color is it? There's a lot of elements to the car that immediately screams, oh, that must be a fast car, that must be fun to drive. But I would argue, and I think you might agree with me, that there's a lot more parameters, a lot more dimensions to the quality of the driving experience. I would argue it's the same thing goes for headphones. That a frequency response is not alone going to tell you everything you need to know about a headphone's response and what it sounds like and what it feels like to listen to it. So in the automotive world, we might talk about acceleration and top speed. We might talk about handling, driving, steering dynamics, braking, and braking distance, the G-forces that is imparted on you when you turn a corner. Right? It's much more than just the way the car looks. And for headphones and for audio in general, I think we're both here to say that it's more than just frequency debate.
And more than just distortion measurements as well.
It's about time.
It's about
I was
time.
going to
Great
tee you up.
segue.
I was going to tee you up that. So the MDAQS algorithm, let me just talk a little bit about that. The background, the motivation for doing this is in part because for a long time, very long time, people knew that frequency responses, THD measurements, distortion measurements were not enough to characterize the full audio experience. Even going back to the late 90s, there was something called PEAQ, P-E-A-Q, Perceptual Evaluation of Audio Quality, that was designed for evaluating audio quality, but really only from the very narrow scope of evaluating MP3 codecs and the encoding technologies. But already then they knew we needed something more sophisticated than just spectrally looking at the signals being transmitted through a codec. And unfortunately, since the late 90s, people still try to take PEAQ and sort of cram that into the shoebox that is acoustic transmission, and it just doesn't work. And so part of the motivation was we wanted to develop an algorithm that could really represent the human experience, the perception of listening to audio and evaluate it. So that's sort of the background behind it. Now, what is MDAQS? So MDAQS is what we call a MOS metric, mean opinion score. This is like acronym soup up here, but MOS, mean opinion score. The mean opinion score metrics all have a similar background in that they are rooted in subjective listening experiments. So at one point, there was a large study where people were asked to listen to something. In our world, they're listening to something because we're dealing with acoustics. And we take the data that they report and essentially build an algorithm around what our subjective participants, the jury participants reported, so that the algorithm can represent that jury in the future. We have, so head acoustics, very personally, selfishly, head acoustics has a very strong background in psychoacoustics, in hearing models, so we start to talk about the perception that happens behind the eardrum. How do we take a physical phenomena at the eardrum and convert that into an impression? Most of that lies on the voice quality side of things, communication quality, and now into the audio quality side of things. So we have 30 years of experience conducting experiments like this, building algorithms around subjective feedback, and constructing something that we can use in the industry that eventually gets adopted and standardized worldwide. Now, even though we have so much experience with mean opinion score metrics, we learned a lot coming up with MDAQS. So I'm going to give you the 5-minute version of 6+ years of research. This slide tells a lot about what we have accomplished. So the first thing is when we ask people to evaluate audio quality, so unlike speech quality, we don't have a good internal reference for whether things sound good or not. In the speech quality world, we can ask people on a scale of 1 to 5, or 1 to 10, or 1 to 100 to rate something, and the average person can do that very well. But for audio, people have a harder time doing that. And so our very first lesson was we needed to use what we call a comparison category rating, CCR, rather than an absolute category rating. So now we present people with sample A and sample B shortly after each other, and then we ask them to compare the two. And we get a difference rating. So rather than on a scale of 1 to 5, we get a scale of -3 to +3. Basically, do you strongly prefer sample A or slightly prefer it? Be somewhere in the middle, and so on. So from sliding from one to the other. That's what this one says. That was the first thing. Now, there's lots of data. People have been working on how to translate comparison category data into objective scales. The University of Washington did a paper on that in 2011. I think we referenced that a lot in our MDAQS research. Either way, that was sort of the first hurdle. Another one was, how do we figure out what people appreciate and listen to and evaluate when it comes to audio quality? And what we found out, again, years of research, was we can boil this down to 3 different dimensions, is what we call it. So there's timbre, distortion, and immersiveness. Those 3 dimensions, if we can accurately characterize, or rather, if we ask a person to accurately score or rate a product on those 3 dimensions, we can accurately predict what their overall quality perception would be of that one product. That's what we found out with the subjective jury study. If we can have people be truthful about their experience in those 3 dimensions, we know how they would feel about the overall product. Now, a cool thing about using the CCR, comparison category rating, is if you're asking somebody to evaluate 3 products, product A, B, and C, and the jury participant says, oh, A is way better than B, then later on in the sample they get to, oh, B is way better than C, and then they get the later comparison, oh, C is better than A, we end up in what we call a circular triad, right? And so we already know when we're doing our listening study, when we're doing our jury studies, everybody who reports scores like that, we throw them out because their data, they are what our developers call human random number generators. They're just pushing buttons. They don't know what they're doing, and they're not reliable sources. You can't do that if you're just doing absolute category rating because they're just inputting numbers, and so you don't know. But by doing it as a comparison, inherently we end up with very valid data because we can immediately dispel all the garbage. Now, when it comes to what these components or these dimensions mean, timbre, as you might guess, a lot of it has to do with spectral information in the signal. Frequency response is a big part of timbre, but you also know, if you are musicians, timbre means something more than just frequency response. Strumming a guitar or just a note on a guitar and hitting a key on a piano might produce the same fundamental frequency, but they sound very different. That doesn't have to do with the spectral content of that note, but it has to do with more. It's the timbre of it, it's the sound of it, it's the feel, it's the richness, it's the harmonics. There's more to it than that. And we have something that we call spectral fluctuations. So it's the fluctuations of the spectrum over time that we use to evaluate timbre. But to boil it down, frequency response is a big part of timbre. Distortion, as you might guess, is all the unwanted stuff that's in the reproduction. So if you're listening to a pair of loudspeakers, if you're listening to a pair of headphones, if there's stuff in there that shouldn't be in there, that's really what people lump into this category. And then immersiveness, that's one of the harder ones to really pin down and quantify. Part of the reason why we're here is because this has to do with the source width and position when you're reproducing the sound field and how crisply it's reproduced and repositioned and synthesized in space. If you're listening to content that was recorded using distinct and discrete locations, like an orchestral piece or an actual 4-piece band, you know where the guitarist ought to be. And if the reproduced sound is able to reproduce the localization of each of these instruments crisply and directly, that's something that's going to score well here. Some people call it imaging or sound staging, and it doesn't necessarily mean how wide it is. It's more about how crisp and how tight it is in the reproduction of that. As you might imagine, a lot of that has to do with the time domain component of human perception and the time waveform analysis component. And this is where technology like MEMS microspeakers come into play, with how crisply they can do that. Now lastly, the overall quality, it's not a sort of an average of that. There's actually a whole neural network linear regression model behind it, but it relies heavily on these 3 dimensions to then predict the overall sound quality. Really quickly, because we are losing time fast, the structure of MDAQS is that we use real music signals during our listening study. So people didn't listen to sine sweeps or pure tones or pink noise, they listened to real music. Those same musical pieces are used in the algorithm. That means when we are measuring headphones, we are measuring them in a realistic state. We're playing music. This is what we listen to. This is what the end user would listen to. This is what's being used during the data analysis, the data capture before it gets processed. So there's a couple steps, boiled down real quickly. There's a pre-processing step. We do some time alignment, sampling rate, normalization of levels, that kind of stuff. And then each of the 3 dimensions get calculated. We, in the process of designing this algorithm, we had over 100 different parameters that we were evaluating for each of these dimensions. In the final implementation, the commercial version of MDAQS right now, we have boiled it down to about 5 parameters for each dimension that we use. So based on those 5, we're able to evaluate or analyze the timbre dimension. Based on a different set of 5 parameters, we're able to evaluate distortion, and then a different set of 5 parameters, we can evaluate what people would think of the immersiveness. And knowing those 3, we can do the combination scoring to get us the overall quality predictor. So from a consumer, you might be interested in just getting the overall number. As an engineer or as a designer, you might be interested in the overall number, but certainly also the individual parameters. So as you're going through your tuning stages, this is where the MDAQS algorithm might give you some insight into what it is you need to tweak and tune along the way to optimize your performance. So knowing a little bit about the priorities, what's being valued, what's being weighted for each of these dimensions can help you as an engineer and as a designer improve your product. So consider this a way to have 300 of your best friends come in and listen to your product and give you feedback, but it's done like that as opposed to collecting 300 of your best friends and getting them to listen to your product and then having to deal with the data collection at the end of it. That's essentially what this algorithm does.
What music is being used as input stimulus?
So the music pieces that we used were 6 different genres, ranging from classical to rock, pop music, bluegrass, R&B, and I'm missing one genre, but it's basically broad genres of music that would represent sort of all different kinds of flavors of music, from the hard rock, like dynamic range, like no crest factor, it's just maxed out, to the classical piano style music where we're really keen on trying to hear the individual notes on being played on the keyboard. So if you ever get a chance, and I should maybe bring a tablet next time where I have the jury so you can listen to the music pieces, you can go through this process of listening to a few different samples and just getting a sense of it. Those that participated in our jury studies, they were presented with 90 different comparisons, by the way. So we had 90 different comparisons and they were offered a break in between so as to not make them too fatigued. Or
the original jury testing, was that done in person or online?
in person.
Okay. Follow-up question. Is that jury testing now closed, or are you interested in gathering more data? And if the answer to that is yes, would you consider holding listening juries at CanJam events around the world?
Yes and yes.
Okay.
That is my dream, but I don't sit in product development. So I would love to collect more data, and especially from this audience that frequents CanJam, because they tend to be a little bit more critical listeners as opposed to maybe the average consumer.
Thank you.
You're welcome. And we would always be interested in more data. Yes?
Did you say you had 100 data sets for that 100 people who actually listened to it? 100. How many people do you actually interview? Is it, I think you said 100. The size of the jury.
No, the size of the jury in the end, it was over 250 people that we ended up using their results, like the results from over 250 people. Each of them had 90 different comparisons to do. Yeah. We interviewed more than that, but there was quite a few that fell into the circular triad trap and we dismissed. Yeah.
Actually, just on that, what percentage of the people did you kick out of the study because of that?
I don't know. But it was more than one.
Well, I mean, is it like half the people can't tell, or Or
No, it's a good question. Generally, my sense was it was not that low, even though we were using untrained listeners. So the requirement for participating in the study was they shouldn't have any professional audio training. They could be audiophiles, they could enjoy music a lot, but they really shouldn't have been trained in the discipline of music or audio or anything like that. So they had to be general consumers, but they could still be audiophiles. We didn't record that element.
So quick question.
Yep.
So on this algorithm you produce, do you actually invite sort of headphone manufacturers to use that so they can assess how good their headphones is as a scale? Is that your business sort of motivation? Is to sell that service to manufacturers? Is that your business?
That's correct. That's correct.
Do you find that that's a conflict between someone paying you to give you a higher score, so they'll come back again to have all their headphones tested? Is there a conflict there?
Well, as a customer of theirs, I can speak up about that if you don't mind.
No, I'm just saying, is there a conflict?
I'll give you actual user experience as a client of Acoustics. We're here because they were 100% honest. If they couldn't get a fit and the design was a little off, maybe we got to go back and revisit the size of the tip or the relationship of how the tube exits the IEM into the ear. Fitment into the head, you need to get a seal. Right? They were giving constant feedback and letting us know exactly what was happening along the way. There was no like, hey, if we did this, you'll get a better. No, they're a test and measurement company, so they're calibrated to a standard of ethics and behavior that is professional at a minimum, and probably even very direct and honest. So you get the good and the bad and the ugly if that's what happens. And so in our experience going to their lab in Michigan, we learned quite a bit by that open and honest, and we're invited to go in the lab. We're there as part of the testing, take pictures, it's all part of the program.
So I have two comments to that. The algorithm is the way the algorithm is. So, we have done the initial jury studies, we built the algorithm around those studies, and it spits out whatever it spits out. We're not touching anything in the algorithm now. So if you bring a pair of headphones to us and it measures whatever it measures, that's what we didn't do anything to it. That's just what that jury sample, how that jury would have evaluated the headphones that you brought to us. So be it. Another thing was we did actually have a separate study with about 20 people that were trained in audio go through the same exercise, and they were kicking and screaming about they wanted more dimensions and more scales and more granularity and all that because they felt like they could hear that. But when sort of gun to their heads, pressed them and said, just do this, their feedback was generally in line with our overall average consumer base. And so we felt like from this very small study we did with actual trained people in the audio industry, this still held up fairly well. But there was a struggle with those guys. Yes?
Sorry, there's a lot of questions.
Yep.
But so I guess I'm just trying to understand, how are you applying the subjective, measurements from the people that did the survey, if you will, and how do you apply that algorithm to like a measuring device, like a new product? Like
Yep.
how do we come up with the MDAQS scores for?
Yep. So we have all that data. From there, we would create an algorithm that accepts a binaural signal on a mannequin. So we have our own mannequin, B&K has a mannequin, Grass has a mannequin. We take a binaural signal that's captured on a mannequin, and then we feed that response into the algorithm that we have built that simulates the jury input. So if the jury is presented with sample A from the product we just measured, how would it sort of rate relative to everything else, and then we can do the conversion into an absolute scale and give you the output along with all the different dimensions.
And we'll show some measurement results in a few slides.
So all the measurements are binaural recordings on the head and torso. And the binaural aspect is also important. I mean, you can't do immersiveness unless you have 2 ears, but we also have 2 ears, and we always listen with 2 ears, and it's more than just a single-sided frequency response. This is a binaural measurement. Yeah.
So if one wanted to use this system to evaluate recording quality, can WAV files be put into the system directly, or the signals have to be captured electroacoustically through the mannequin?
Good question. Electroacoustic measurements using a head and torso.
So that's the input.
Right, so the pros and cons of doing a MOS metric, any MOS metric, is that the algorithm is really only good for what the jury was asked to do. So if you start to feed it signals that just went through some kind of recording process, that's not really what that's not what the algorithm was designed to do. It was designed to evaluate acoustic signals.
So
captured by Morley.
Captured in that same camera.
Yep. Yep. Yes.
Am I correct in assuming that this MDAQS works specifically with the dummy head from acoustics?
It does.
Specifically the type 4.4, I assume?
No. No, it is not exclusive to any mannequin. So the algorithm works by taking a binaural signal. In some ways, it's garbage in, garbage out. If you take a crappy, poor binaural signal, chances are the algorithm is going to score it poorly. So we want a high-quality binaural signal captured by a high-quality mannequin, like the ones manufactured by Pro & Care and Head Acoustics, and even the Grass mannequin. Those are measurement-grade, calibrated to industry standards measurement equipment.
I'm asking specifically because the type 4 and the type 2 and type 3, these simulators will have, especially when you measure in-ear headphones, will report significantly different amounts of sound pressure at low frequencies.
Correct.
Due to the different acoustic field, which plays a tremendous effect if you go see a camera. True, the distortion is not different, but just the amount of bass is going to be different.
Yep. So that's probably something that you should report when you are doing your MDAQS calculation. This data came from X test fixture, because just like the test fixtures will record the drum pressure differently. If the drum pressure is different, that's the data the MDAQS algorithm has to work with.
Right. Okay.
So whatever fixture you're using, you have to take that into account. But it's not going to reject data because it was captured on the CSIG guide. Sorry, John. Yes?
I'm curious about the analysis for immersiveness.
Yeah.
What sorts of metrics get analyzed in that? Is it time-based information?
A lot of it is time-based. A lot of it boils down to using hearing models, binaural hearing models, and looking at essentially neurological signals. So how the human brain would take the drum pressure and how the cochlea would behave, how the cochlea would fire those signals into the brain, and how the brain would reconstruct those signals, those auditory signals. That's a lot of what's happening in the immersiveness domain, and it gets pretty in-depth. That's also the metric that takes the longest to compute, because you're taking 80 plus seconds of data and then doing this for a large part of it. A lot of it is PhD level stuff that's beyond me, and it's really comes down to the developers that are deeply embedded in this that can answer those questions. And in the interest of time, I would like to move on, and then I can talk with you later if you want. Is that fair?
Yep.
Okay. Because
it's about time.
Oh boy, it's about time.
Figuratively and literally. Thank you, Jacob.
Sure.
So, what have we done? No shortage in our supply chain for silicon, not silicone, sorry, silicon. And we're fabricating a monolithic speaker using a standard semiconductor process known as MEMS, micro electromechanical system. And this is just an example of how a single crystal of silicon can be pulled up by this several ton crane. And this is a single crystal of silicon, and that is processed down into wafers using a saw to start singulating out different types of wafers. And in normal semiconductor fabrication, where just solid state device and electrons are flying around inside of the silicon, they use photolithography to actually expose and etch back semi and conducting circuit paths within a three-dimensional structure of the silicon wafer. And that's what's been powering the world since the late 60s, is semiconductor devices. However, we do something a little bit differently. So we don't have processing going on. What we're doing is we're driving electricity voltage into a radiator and making it displace, pumping up and down air, which creates sound. And so I'll hand this wafer around so you can have a look at it. And some of these people in the room know the answer to this question, so you are disqualified immediately. But guess how many 20 hertz to 80 kilohertz full range speakers are on this wafer, if you want to have a look around. And what we're doing is we're arraying small facets, small shapes that can be displaced with voltage. And it's a piezo MEMS device. So it's a little bit different than your standard speaker. We all know what a voice coil is. We all know current goes in an inductive coil, and it generates a motor force. The spider assembly precise as the voice coil in the gap. You have a radiating surface area, different shapes. Little dust cap, but you also have a rubber surround around here. And so this system has a spring mass relationship here, where you have some different materials, and the mechanical tolerance stack up of fabricating these individual pieces, the adhesives and glues that hold this together, result in small dynamic drivers, even a balanced armature. They call them receivers. I still don't know why, but it is a small speaker used in hearing aid industry. And also a lot of IEM manufacturers on the floor are using several IEM or BAs in their IEMs. And USound is represented here. They also do piezo MEMS. They have a piezo MEMS actuator, so their motor is capacitive voltage driven, just like us, requiring 10 volts of E-bias to put the sound into the system. But where there's a little bit of differentiation is our system's completely monolithic. So analog audio will come in, and because of the monolithic fabrication process, the motor is the radiator. The motor is the speaker. The driven area moves, not on the end of a cantilever or in the center of a larger system. And so when voltage goes up, we obey. When voltage goes down, we do the same thing. There are bypass gaps in the individual radiators of our system because we can't have the individual elements touching each other. And so this generates the bypass gap, and there's also some back volume here under the semiconductor device. So I'll hand this around. Please don't open the case. We don't want these to fall on the floor, but you can have a look at some of the speakers as they're packaged. So once the wafers are fabricated, we test the die. We go to packaging, and we produce some speakers. You'll see on the wafer, you'll notice this shape. When you look at the wafer, you're going to see 6 squares, and each one of those 6 squares is made up of 4 trapezoids. So there's 24 radiators in one speaker on that particular wafer, but we have different devices. We can work with different shapes. You can see a spiral here. We have others that are much larger shapes. We call them cantilevers. This gives you a console model visual representation of the actuation, which you can see through. So it's not a solid diaphragm. So the pressure on your eardrum is a little bit different. When you listen to these in the bass range, you get excellent resolution. I'm a bassist and a DJ, so I love low end. And the accuracy in the bass response is that I haven't heard before in an in-ear. Any questions about this so far? So I mentioned there's a couple different design types. we were able to iterate on our original constrained peripheral system, and we went to something that has higher volumetric displacement. So the radiators are possible to travel higher and lower, made them larger, and we also were able to make them smaller because we have a higher sensitivity with this geometry as we do in a constrained peripheral geometry. And so that allowed for more bass response and higher volume. But really, you know, something happened to us in, I guess it was 2 years ago. A big tier 1 manufacturer asked us to build a set of earbuds that had the Harman curve. And is there a microphone? Yeah. Check. Is this working? Thank you. Yeah, so a manufacturer had asked us to produce a set of demo buds that had the Harman curve, and we did that. They tested against their premier product that was on the market, which also had the Harman curve, and they did some additional measurements, and it was several weeks went by, and they came back to us and said, well, your distortion's a little bit higher than we like to see, but somehow all the engineers like the way your drivers sound. Why? How can you have the same frequency response, technically worse distortion, but every single engineer on the team won't pull these out of their ears? Because it's not about magnitude and distortion. Well, it is to a degree, but now that we have a transducer that's almost as fast as the microphone that recorded the signal, the delta in the time domain of these transducers is astonishing. And our brains, I believe, like phase correlation to be accurate. And I think that the coil-based transduction we've been listening to for years is not accurate in the time domain. So how is that possible to prove? So I went to a mastering engineer in LA, Brian Lucy, and he's 8 or 9 Grammys, and he's working with Dolby and Apple, converting albums into spatial audio for iTunes. And I was at his studio. He had a demo pair of earbuds, which I have with me today, 3D printed by us, nothing inside, no DSP. We just had our CanJam. And he had just came back from doing some work, and he's working on a John Legend album. And he was listening to the Dolby Atmos rendering, and he kept pulling in and out of his ears, and I was getting scared. I was like, oh my God, he hates these things. And then he's like, I'm hearing something. I was like, okay. And then after a while, he put it on his big main speakers, $250,000 rig, just amazing, all tuned and certified by Apple and Dolby. And then he's listening to Odyssey and Sennheiser and all these different headphones, a $30,000 DCS DAC. And here's my little giveaway amp with a battery and these 3D printed shells. And he's like, I think there's a problem in the binaural release. I'm like, what are you talking about? Well, Dolby releases updates on Atmos all the time, and we just got a binaural release, the down mix into stereo. I'm hearing shoo, shoo, at this part of the song. So he calls the guy who tracked the session. He says, hey man, can you tell me if I didn't hear nothing. And he's listening on the speakers, we don't hear it. On his planar magnetics, on his other speakers he didn't hear, but on our little giveaway 3D printed earbuds with nothing inside but our speakers and some wire, he was hearing this phase issue. So we called Dolby and said, hey man, you guys should go to the AES show and talk to xMEMS because you need to be checking your software with these things. So we were just thrilled. But why? Well, what's going on? Well, it's the impulse response. So this is an example of our MEMS performance. So yes, it can move, and yes, it can stop without a lot of side ripple. But here's a Sennheiser IE800, and at the time, this was the best dynamic driver we can have that musicians respect and audiophiles have been listening to for a while. It just cannot stop and slow down when the signal isn't present. It continues to store energy in the time domain. So this is called a CSD plot, and in blue coming towards you is time. This is frequency. So our resonant frequency in the MEMS drivers is pushed as high up to 20 kilohertz that we can get, but you can see where the resonance of a standard dynamic, high quality dynamic driver is. It's right in the middle of the audio band, and this is stored energy. And as a bass player, I'm like, I didn't play that. When I stopped playing and I muted my strings, or I shut off my rig, there should be none of this. But it's there. So what we did is did some comparisons with not only a hi-fi dynamic driver, but we also did some comparisons with an ANC premier consumer product and some other products. So what we have here in this panel is group delay or phase shift. So when you have one device, one speaker, you can measure its mechanical performance with an input stimulus to a displacement. However, what we want to know is, do these parts have variation in phase? So this is a Bose Quiet Comfort. We harvested the dynamic driver out of a Bose Quiet Comfort TWS earbuds. And you can see that they're pretty flat in phase, but they're in the millisecond domain. Our speakers are so fast, they actually get faster over time as you get into higher frequencies, that they're in the microsecond domain. So they're a lot faster. What does that mean? Jacob talked about spectral harmonics and the quality of sound. I mean, a violin, a viola, a bass, a keyboard can all play A at 440. How do you know the difference between those instruments? It's the spectral content, the decay, the attack, and can your harmonic that's maybe way out, way higher up, maybe people say beyond our hearing, what contributions does that have into the resolution of the room that was recorded in? The decay time of the room is really well represented. So in relative phase, the absolute measurements, and then in relative measurements, we compare it against some popular stuff here. And what you see is fairly flat accuracy on where people can judge where sound is coming from. So we call this azimuth judgment error, and you can see traditional dynamic drivers, they do change their phase characteristics over frequency and amplitude. Any questions about this? Yes, please.
I'm just noticing on your CSV plot there that the time information is in a different spot. And I'm wondering, is the suggestion that if they were in the same spot, there would be less of that with the MEMS driver?
Yes.
Okay.
Yes, that is a fair conclusion. And so we measured some of these 3D printed buds. What this is just something we glued together. So we're using the side fire port. So the top fire has the holes in the top for emanating the sound out the top. And you can't really see in the video or the image here, but there's a slot here where the sound comes out on the side. So those are the ones we used. And you can see that just because the fabrication process locks together the sensitivity of the devices, you can see that their sensitivity matched all the way out. So this is a 711 coupler, so we won't look at this as accurate to acoustic impedance of the human ear, but up to 10K. But the other suite that you see here is the relative phase of both earbuds. So these are holding a couple of degrees of phase in the delivered package. We knew that the device by itself on a bench was awesome, but having it just go into some earbuds and hold that phase is astonishing. Yes, please.
How's the variability wafer to wafer? So I buy 1,000 of these devices, whatever number comes off a wafer, and then I need to do another order, and it's the 1,000th wafer later. How well matched are they?
Extraordinarily impressively matched. Yeah, we're holding, what we put on our data sheets is chosen by marketing, but what we can do in reality is much tighter. But yeah, they're within sensitivity, they're completely matched. Within a dB, we could say dB and a half on the data sheet.
What about on the phase match?
Well, let's go back to this previous slide here. And then, so we're looking at a deviation. We've measured this with the Polytech system out to 10K. This shows out to about 3, but we have a data out to 10K, plus or minus 1 degree deviation device to device, so 2 degrees. And so how can I prove that at the device level? So that's why these sweeps are really impressive, because so this axis was cut off. This is a 185 degree scale. So pretty tight. And then, so I have other pairs. Here's the distortion. Sorry, I want to mention Steve Temmie's name briefly, but he taught us about normalized THD. There's a little bit of a THD. This is what one of the tier 1s saw. Like, hey, you're getting up, you're getting close to 1.8% distortion. What's going on here? But our frequency response over sensitivity, or our sensitivity over frequency response increases. So, of course, the harmonics are going to be measured with a standard THD equation louder than the fundamental, because our speaker is getting louder with the same input stimulus. So we're being penalized for showing up on a THD plot with a higher harmonic measurement. So when we do normalized THD, you can actually see that flatten out.
5 minutes.
5 minutes, okay. Well, now here's a different EQ curve. We put an EQ in there just to kind of tune the highs a little bit, just to see if putting some biquad parametric filters into the system would deviate the phase. Not so much. So still holding pretty tight phase even after some DSP processing. And THD for that EQ curve. So since it's voltage driven, we've got to take the millivolts RMS from the headphone amp, analog input, and we have to boost it with the boost converter, and this will put plus 24 dB of gain into the system. So as you turn up the volume, you're taking millivolts RMS. Our little amplifier will create the V bias for the diaphragm, which goes out on the output, and then we will boost the volts peak to peak into the wafer or to the die to actually actuate. And this is one of our speakers with the complete amplifier and bill of materials on the back. So think of this as a powered monitor for your ear that you can rapidly prototype with. So there's some links here. Brian, Lucy, you're kind of talking about phase and why it's important. Some people you may recognize from CanJams I've chased around saying, please listen. They're starting to get it. And so just to show some results, I'll put it over to Jacob. 2 minutes.
Oh boy. Yeah, so we, Michael and I worked together to grab a couple of measurements and results because a lot of the stuff that we were seeing with the traditional measurements weren't really documenting what people were hearing with the xMEMS devices. So we went to the lab and Michael brought us what is like the simplest possible earphone. Michael, what is it? It's a couple wires and a transducer.
UV glue, some wires, and some SLA 3D printed housings.
And so basically the point is that we're starting to see that just using good transducers gives us a really sound fundament to really start building products on. And we had a couple different versions, or Michael brought a couple different versions with him. Super simple stuff, but it gives us some good bones to work with. And now just to compare, this is a commercial TWS. There's lots of DSP and engineering that went into making this product. And it's a good product, but it still has some limitations, even if it nails the frequency
I don't think
response.
they give those away for free as
They don't.
samples and don't build them in 5 minutes.
No, they don't. So the point was, if you then take some of this technology that Michael's been working on, and you actually spend the engineering dollars and the engineering time to put together a more polished product, you end up with something that measures well, that sounds well, and that we can now also really start to see that the objective measurements are going to score well also. So the two products here, can we mention them?
Yeah,
People might recognize
they're on the
them.
market. They're being launched at the show, so
Right.
they're being announced today. So, yeah.
So we took actually quite a lot of devices. There's probably 20 some devices in here, all normalized to 1K, but the point is we had a broad selection of devices. You can see the frequency responses all vary. So there's a lot of stuff in there. Half of them are over ears, some of them are in ears. And if you squint, they all sort of follow the same trend. But how do we make heads or tails of which is the best, which is the worst, which one would we like, which one would we not like, just based on that? And it's hard to do. And I apologize for this, eye doctor seeing eye chart here. But the point is, if we make the assumption, and I think it's a valid assumption, that if you don't have a good frequency response, you have nothing at all. That's true. But if we weight everything on the timbre dimension, where frequency response is most heavily favored, all of these, first of all of these are really fantastic products. These are all, this is the upper echelon of products. Broad variety, but upper echelon. They all score well, and I've ranked them according to their timbre dimension on the far right column. If we sort that according to the overall, what you see is the top 10-ish products, they're still up there. The top 10 still score really well, but there's more to it. And you start to see the shuffling, and that's important for two reasons. Number one, as I mentioned, you can't have a good product without nailing the frequency response. It has to be a good frequency response, otherwise that's the invitation to the party. Otherwise, go home, start over. Number two, though, means there's more to it. There's more to the perception than just frequency response, and I think this is where we ended, because we believe it's about time. That's it.
Yeah.